separate slide, is notice that each core has its own cache, an L1 cache on the system. And notice that there's a separate L2 cache that generally is something that is shared between the cores. So as you start looking at some of these newer styles of CPUs and the newer architectures that are out there, you'll see that these dual core technologies are often set up this way, where there is a separate cache per core and then a larger L2 cache that's just outside that handles all of the cores that happen to be on those systems. Today you have processors that have multiple cores. They might have 4 cores inside of the system, might have 4 separate L1 caches, and still one individual L2 cache that handles all 4 of those cores. Once we need to gather information that's not in the cache, then we need to go out to system memory. We were talking earlier about how that cache allows a CPU to perform calculations very, very quickly as long as that information has already been gathered from the external bus memory that's out on our motherboard and copied into cache. And so the CPU doesn't have to go all the way out to the system memory and gather that again. We mentioned that it's a relatively slow process to do that. And that's because the CPU has to jump through the memory controller hub across the front side bus, or the FSB. We talked about the FSB in an earlier module. That bus actually consists of 2 different pieces. There is an address bus and a data bus. And the way that this works is the CPU is going to request the memory address through the address bus, and so that the memory controller hub knows where to grab the information finally from the random access memory. Once it determines what it needs to grab, it sends that information back over a data bus. And you'll notice that the address bus and the data bus may have 2 different sizes associated with them. Sometimes they're exactly the same size. Both of them might be a 32-bit bus, for instance, but that's not always the case whenever you're looking at that front side bus and the way that the address bus and the data bus are related to each other. Another piece that I put into this diagram is a clock, and I put a picture of a metronome. If you've ever sat in front of a piano or worked with music before, you know that a metronome is there to keep a constant rate so that all of the systems that are inside your computer all are running across the same clock. And so that it knows the CPU sends this information, it knows when to request, and it knows when to expect to receive information, because the clock is keeping time for everything that happens to be in your computer. There's a clock for the CPU, there's a clock for the memory controller hub, and everything happens in step. Everybody's on the same time schedule when we're dealing with these different components inside a CPU and inside the motherboard itself and all of the different components. Now, what you're going to find when you start looking at that is you'll see on your motherboard itself the clock. That is a picture right there of a clock that happens to be on my motherboard. And you can see it's running at 40 megahertz. 40.000000 megahertz to be completely accurate here. Well, we know that the CPU that's inside this system is running at 1 gigahertz. So how is a clock that's running so slowly, relatively speaking, keeping up with that? Let's look into that a little bit more. Inside that little device we were looking at is a quartz crystal. It's extremely accurate in the way that it works. It's an analog signal that we have separate chips on our motherboard that convert that analog to digital pulses so that all of the systems stay in time. It's, as we noticed here, much slower than the actual CPU. That's because the CPU is using something called a multiplier. And for our particular clock that's on this motherboard that runs at 40 megahertz, if I have a 1 gigahertz CPU, which is really 1,000 megahertz, then we know that the multiplier inside the CPU is really 25 times faster than this other quartz crystal that's on the system. The reason that these are separate is because if we wanted to use a different speed CPU, well, that would probably mean that we'd have to then remove this particular quartz crystal and replace it with one. That's a little bit of a problem sometimes. Often you'll find a motherboard will support many different speeds of CPUs. Also keep in mind that the buses that are inside your system are also running at different speeds. The ISA bus is also running at a different speed than your front side bus. And so all of those systems, to be able to run at different speeds, simply use different multipliers, but they all keep track from exactly the same clock. A CPU also uses different modes to operate. You'll often hear these terms used because this is the way that our operating systems use the CPU. The first mode is called real mode. You'll often hear this referred to as compatibility mode. And that's because this was the first real method that CPUs used to operate back in the 8088, 8086 days. There is no memory protection built into the CPU hardware. Everything is really wide open, which means that one program could perhaps accidentally use memory that was being used by a different program. And as you can imagine, these applications sharing memory that way can create major problems and crash the applications themselves. And that also meant that in the hardware itself, we weren't able to do any type of real multitasking. When processors evolved and introduced in the 286 and really became usable in the 386 chip, we have something called the protected mode. This really launched the ability of Windows and other operating systems to be able to really multitask properly. And what this allowed was that the CPU could now handle this process of multiple applications running at the same time, and it had a way to protect those applications from overwriting each other. Therefore, it's called protected mode. This greatly changed the entire PC platform technology. At this point, Windows was really able to take off as an operating system, and that changed the way we use computers forever. Let's review what we've talked about then. We know that we've gone through exactly how a processor is constructed. We looked at that architecture and we saw how all of the different buses interacted with each other. We looked at the way cache memory is associated with all of those things, and even went into a little bit of the detail with registers and how the math coprocessor or the floating point unit is now used. And finally, we understood a little bit more about how real mode and protected mode are used inside a computer and how it really changed the way that we're working with our computers today. For more CompTIA A+ videos, for study guides, for our online message boards, feel free to visit our website at freeaplus.com.